Okay. So, let us continue from where we left the proof yesterday. So, we wrote this theorem for the maximum, minimum and saddle point test in terms of the Hessian matrix. Instead of calculating the eigenvalues, we just look at the principal minors of the Hessian matrix, and then decide we will be able to decide the some critical point is the maxima, minima or saddle point. So, what was the theorem? So, I have the same setup, f is from an open set to R, P is a saddle point in U. Instead of writing H f p repeatedly, I just denote it for this theorem A equal to H f p, because once P is fixed, F is fixed, I can just call it A, and A k be the kth principal minor of A. So, you have defined kth principal minor, that is the first k row and first k column you take and leave rest of the part, and of course, you can see that A n is equal to A, nth principal minor is the entire matrix A. So, what is the test? Well, if for some 2k, some even number, the principal minor A 2k, the determinant is 0, then P is a saddle point. Now, if we have determinant of A n not equal to 0, that is to say P is a non-degenerate critical point, that is A n is invertible matrix, Hessian is an invertible matrix at P, then P is a local minimum if and only if every principal minor of A has positive determinant. Similarly, P is a local maximum if minus 1 power k determinant A k for every k is greater than 0, and of course, if determinant of A n is equal to 0, then P is a degenerate critical point, and in that case we cannot conclude anything about second derivative test, anything from second derivative test. Second derivative test fails, we have to do something else there, we have to go for higher derivatives, or maybe we have to do something by observation. I forgot to note something yesterday, that actually we are dealing with non-constant functions, because constant function grad f is 0 for every p. So, there is no test for that, and so actually I can add here that P is a strict local minima, P is a strict local maxima, that is there is no point nearby in the neighborhood where it is equal to f p. Okay. So, what about the proof? In the proof, let us in A part. So, let us have determinant of A 2k less than 0 for some 2k between 2 and n. I have denoted P with this coordinates P 1 to P 2k, 2k plus 1 P n, and Q is P 1 to P 2k. So, I have chopped up this 2k plus 1 to P n part. Then we define this open set in R 2k, which is x 1, x 2, x 2k, that is such that x 1, x 2, x 2k augmented with P 2k plus 1 to P n. See that P is fixed. So, these coordinates are fixed, that belongs to U, and we consider this function g from V to R, which is g x 1, x 2, x 2k is equal to f of x 1, x 2, x 2k. This is a free variable, and this 2k plus 1 to n are fixed. Then it is very easy to note that since these are fixed, that Hessian matrix of G at Q is del square f del xi del xj k cross k matrix, which is precisely the 2kth principal minor. Now, under the assumption that okay, we have assumed that all, I think yesterday we wrote down that all derivatives, all second order partial derivatives are continuous. This is a symmetric matrix again. So, A 2k is a real symmetric matrix, it has 2k many eigenvalues, maybe with repetition beta 1, beta 2, beta 2k, some of them may be equal, but I can write counting multiplicity, I can write 2k many eigenvalues, and all of you know the determinant of 2k is the product of the eigenvalues, and this is given to be less than 0. Now, here comes the catch, that I have even number of real numbers here eigenvalues whose product is less than 0. So, that says that there must be one which is positive and there must be one, because if all of them are negative, since there are even number of terms, the product will be positive, and if all are positive, product is anyway positive. So, I can conclude from here that there exist I and j such that beta I is negative and beta j is positive. One eigenvalue negative, one eigenvalue positive. Okay. Given an eigenvalue, I can of course talk about, I have a corresponding eigenvector. So, let u be a eigenvector for beta I and v be eigenvector for beta j, that is h g q u equal to beta I u and here h g q v is beta j v. Where is u and v? U is a vector in R2k, v is a vector in R2k, right. Okay. Now, just consider this vector y1, u1, u2, u2k and 0 up to nth coordinate 2k plus 1 to n, and y2 equal to v1, v2, v2k and rest of the part 0. So, these two vectors are in Rn. So, 2k plus 1 to n coordinates were missing there. So, I put them 0. Okay. Now, look at what happens y1 prime a y1. Y1 has this coordinate 0. So, this will be how much? You just calculate, this will be u h u a2k, which is h q u, which is equal to, so this is a, I should have written a here, right, a2k here. Which is equal to beta I u prime u. Now, it does not matter if you take u norm 1 or not, u prime u is always positive, or all the time you can take norm of eigenvector is always norm 1. Usually we take eigenvectors norm 1, in that case u1 u is 1, which is beta I, this is less than 0. And what about y2 a, y2 prime y2? For the same reason, this is v prime a2k v, which is beta j v prime v, which is beta j bigger than 0. So, what we conclude? Okay, now something is less than 0, something is bigger than 0. I can make u was norm 1. So, y1 and y2 both are same norm as u, because I have just added 0. That implies minimum of y norm 1 y prime a y is less than 0, less than maximum v equal to 1 y equal to 1 y prime a y, because there is something positive, one vector for which is positive. So, maximum is bigger than 0, one vector which is negative. So, minimum is less than 0, and you remember this is precisely the condition for P is a saddle point. Okay. That is the proof for the A part. B part 1 and 2 is very easy, that is direct from linear algebra. You can check it with your linear algebra notes that this is simple linear algebra. Determinant of A k greater than 0 for all k implies all eigenvalues of A are positive. That is to say, this is if and only if the minimum of the eigenvalues is positive, this is if and only if P is a local minimum. Okay. And once we have one part for local maximum, consider minus f, and we have already observed h of minus f at P equal to minus hf of P. So, A2k for minus A2k corresponding to the principal minor principal minors of principal minors of order k corresponding to f is negative of principal minor corresponding to minus f, and you know determinant of this is simply minus 1 power k determinant of a k. So, apply 1, you will get P is local maximum, because a local maximum for f is a local minimum for minus f. Okay, that is the proof. Very good. So, this gives you one way to check the nature of this critical point, saddle minimum or maximum. For the rest of the today's lecture, and that is the end of this third module, we will specialize this theorem with examples of course to n equal to 2. I will directly apply this theorem and see what happens. So, specialized to R2, that is, now I have a function f from an open set U in R2, which is only 2 variable to R. In R2 you will see most of the books use some special notation. So, if I have some x naught y naught in U, this is grad f at x naught y naught, which is actually del f del x at x naught y naught, del f del y at x naught y naught. People use some special notation for this. This one is written as this way. So, this is notation only, f x x naught y naught, this is the partial derivative del f del x. Instead of writing this, one writes f x for R2. So, this is, so I am following some book notation, standard book notation here. Okay. Similarly, del square f del x square, this is denoted by notation again f x x, and del square f del y square equal to f y y, and del square f del x y del x del y equal to f, first you doing y, so y x, but we are actually assuming that they are continuous in our. So, this is f x y, first x then y. So, these are the notations, special notations for usually used in books, they are same thing, right. And this Hessian matrix at x naught y naught is usually again denoted by this delta x naught, y naught, which will be equal to now in this notation assuming second order partial derivatives are continuous, so that the matrix is symmetric. Okay. So, what does the test says? Apply the theorem. Okay. What will it say if I apply the theorem? That you see A 2k is even, but there is only one, there are only two principal minor here, delta 1 which is fxs and delta 2 which is delta itself, and I should have some delta 2k less than 0 for saddle point. So, test says A, if delta 2k, but only one possibility, that is the delta itself is less than 0, then x naught y naught is a saddle. Okay. Next, delta not equal to 0, all the principal minors are positive, that is delta greater than 0 and fxx greater than 0, that is if and only if x naught y naught. So, this is the first part. So, this was the assumption B. So, 1, if and only if x naught y naught is local minimum. Similarly, delta, what will happen? All the principal minors are, and what was the condition there? Minus 1 power k, remember, for maximum minus 1 power k delta a k. So, now here I have delta 1 k equal to 1, so I should have fxx less than 0 and 2. So, minus 1 power 2. So, this was the condition is 1. So, delta must be, and that is second principal minor is delta itself, this is greater than 0 if and only if x naught y naught local maximum. So, you just go back to the theorem, apply it, you get this result, and of course, third condition is there, C delta equal to 0, I should have written determinant everywhere, determinant, delta equal to 0, then okay. So, this is so easy to remember. So, max delta determinant greater than less than 0 saddle, both the cases determinant is positive, and so it is determined by the sign of fxx, fx is greater than 0 local minimum, fx is less than 0 local maximum. Now, I will do two quick examples. Instead of doing just writing one function, I do it with some problem where we can apply these things. So, this is a problem, I found it in one of the books. Find minimum distance from the point 0 b greater than 0, that is on the y axis, to the parabola x square minus 4y equal to 0. So, what is the problem? Here is the point 0 b, this is b, okay, and here is a parabola y y equal to x square by 4. Okay. I want to find, so you can draw different lines from this to the parabola, different points. You have to find the distance, that is minimum distance, that is the length which length has the minimum distance. So, for that I have to find out a point on the parabola for which this distance between these 2 points are minimum. That is what we have to do. So, how do I start? So, let x naught y naught be such a point, be the point on the parabola where minimum distance is attained. Okay. Now, what is the distance? I have to minimize this distance from 0 b to x naught y naught, which is equal to x naught x square, any point on the parabola, x square plus y minus b square, where y square equal to 1 over 4 x square, because it has to be a point on the parabola. Now, if you see, this is a distance is a positive function. So, instead of minimizing this distance, I could as well minimize distance square, that will minimize distance as well. So, I can get rid of this root over, so that I have some derivative calculation is easy. So, this information will give us, this is x square plus x square by 4 minus b square, which is x square plus x power 4 by 16 minus x square b by 2 plus b square. So, this is a function of x only. So, you now see you have reduced the problem of minimizing a function of 2 variable x y to a function minimizing a function of x only. I want you to complete this yourself, because now you have to check, you have to find a point x naught such that f prime x naught equal to 0 and f double prime x naught is minimum, so greater than 0. Once you do it, you will find that there is some fun in this problem, in the sense that this position of x naught will depend on the position of b. So, complete it. And I request all of you to complete it. That will help you in future in whatever way you understand it. Okay. I have reduced the problem of finding minimizing by 2 variable by 2 finding the minimum of 1 variable function. Second example is also interesting in the sense that, let us see what happens. Let us say f x y defined on entire R2. Two variable function. Let us check for minima, maximum. On the entire R2, u equal to R2. Straightforward, you can say there is no maximum. Why? Because if you keep on increasing x and y, this function goes to infinity. You take x and y as big as you, f x y you can make very close to infinity, I mean it is as big as you want. So, there is no maximum. So, I have to check for saddle or minimum. Okay, let us see a critical point. What is grad f x y? This is how much? 4 x cube plus 2 x y and grad f grad y is x square plus 2 y. So, for critical point 4 x cube plus 2 x y equal to 0 and x square plus 2 y equal to 0, you see that only critical point is 0 0, that satisfies this equation. Okay. This is my f x, this is my f y. Let us see what is f x x. I have to go for the test. This is equal to 12 x square plus 2 y. So, f x x at 0 0 is 0. F x y is how much? First, okay, f y x I let calculate, first x then y. So, f x is this fellow and then y, that is 2 x. So, f y x 0 0 is 0 and I do not need f y y, still I do, it is 2. So, delta equal to, delta at 0 0 is 0 0 0 2, determinant of delta is 0. So, 0 0 is a degenerate critical point. So, here we cannot apply the test, but we can make a little observation, and as I was saying that if the second derivative test fails, one tries to make observation and see if we can still conclude something. You look at this function, my claim is 0 0 is local minima, in fact it is a global minimum, because f of 0 0 is 0 and you see x square y modulus of this is of course the positive square root of x 4 y square, correct. So, this is the geometric mean of x 4 and y square. So, this is less than equal to x square plus y square by x power 4 by y square by 2 arithmetic mean, which is strictly less than, both are positive, x 4 plus y square. That says x 4 plus x square y plus y square is always greater than 0 for whatever your x and y are, but f 0 0 is 0, it is a local minimum. So, in case of degenerate it is not still that hopeless, you can do something. Thank you, that ends the third module.